Yep, let's go. Yep.
Okay. Well, good morning, everyone. We'd like to welcome you to the Eastern Transportation Coalition's The ABCs of Conflation, TMC, LRS, OSM, What Happens When You Muck It Up. Going to go through a few housekeeping items and then we'll get right into it. We are using Zoom webinar today, so you're either connected through your computer or phone. The important part here is this web meeting is being recorded. We have the Q&A box as well as the chat box today. The Q&A we're using for questions. Those are questions for the presenters that you would like to have answered. The chat box is for any technical issues. To use the Q&A, you just simply click on the Q&A button and type in your question. Those questions will be monitored throughout the meeting and will be directed to the presenters to answer. You can keep track of your questions in the My Questions tab that you have. If you'd like to ask a question verbally, you're able to do that too. All you need to do is raise your hand. At the appropriate time, we will make mention of it. We will unmute your line and you'll be able to ask your question. We just remind you that when you're finished, if you can mute your line again. At this point, I'd like to turn it over to Denise Marco from the Eastern Transportation Coalition. She is the TSMO Program Director. Denise?
Thanks, Joanna. Can you hear me?
Yes, you sound great.
All right. Good morning, everyone. Thanks for joining us. This is one of our first, or is our first, I should say, deeper dive webinar. It's really kind of getting into the weeds. It's a technical webinar, but it was a webinar subject topic that had been requested by our strategic planning committee. In particularly, North Carolina had a lot of questions and a lot of requests for this. So in order to kind of do what our members would like us to do, we're holding this a great webinar today. So we hope you enjoy it. Next slide, Joanna. So we have 154 registered from 26 states. We did open this up across the country because of the nature of the topic. And as you can see down below, we've got many different agencies from DOTs all the way across to consultants who are on the call today. So thank you for joining us and we hope you do enjoy the webinar. Next slide. Before I turn this over to Stan Young, who is our Chief Data Officer for the Coalition, we always, as a matter of protocol, give you an update on what the Coalition has been doing lately. So in the recent bullets that you'll see there, from June through July, we've had a strategic planning workshop. That's kind of what I referenced in terms of where this topic came up. We hold a biannual working group, our WAYS technical team. We meet twice a year. So we had our biannual June meeting on the 15th. We talked with WAYS product team and we looked at all the data integration that we're doing with WAYS. We had our state point of contact, that POC means the point of contact meeting for those states that are buying data through our traffic data marketplace. And that's a biannual member, a working group meeting we have. And then we have our quarterly RIDIS user group. So those were the activities that took place in the summertime. Upcoming, what we have right now is we're in the process of doing a procurement for a new marketplace, traffic data. We're actually changing it to transportation data marketplace. So we're in the process of having evaluation meetings with our teams. We have 6 data sets that we're looking at, and we're hoping to get through the technical requirements to the end of October. Meet the Work Zone Data Exchange Project. That's a web meeting that's coming up at the beginning of September. It's a part of our travel information program biannual meeting. And we've invited the Work Zone Data Working Group to come in and to talk about the spec that they're creating for work zones and kind of introducing it to coalition members who have not been part of that project to date. The RIDIS user group, the next quarterly September, we have something called a travel info technical meeting. So what we're trying to do is, as we are developing some of our common data fields with WAYS or with the Work Zone Exchange or with RIDIS, we're then looking at a technical meeting to do a gap analysis so that we can then move forward and approach some of the other mapping companies about what we as a coalition are looking for. The TDADS is the Travel Disruption and Disaster Statistic project that we're doing. That's where we're building the congestion pie chart. That is a national webinar taking place in November because that project is almost complete. And at that point in time, that webinar is going to show all the states, all the data will have been loaded. So each state will be able to build its own congestion pie chart, being added by state level or by county level. So that's that national webinar. And then again, the technical working group with Waze, and our point of contact, so a cyclic process. So that's a lot going on, but just to give you an update, if you're interested in any of this, shoot me an email and we can get involved. Next slide. So just a reminder to use the Q&A box for questions and use the chat for technical. I know sometimes that we forget, but that's just a reminder again, do that when you have questions. We will be monitoring the chat box, or excuse me, the Q&A box. Go ahead, next slide. And so with that, I'm going to turn this over to Stan Young. Stan is he is an urban scientist at the National Renewable Energy Lab, but he has also become our Chief Data Officer for the Coalition, and we are thrilled to have him with us. So this is the first of many data-driven webinars we're hoping for him to facilitate. So with that being said, Stan, I'm going to turn it over to you.
Thank you, Denise, and welcome everyone. I've been looking forward to this webinar, this and the whole series in an area that's near and dear, geospatial information with respect to roadway jurisdictions. Here's our agenda for the day. Denise, thanks for kicking us off. I'm going to give a quick background after this, kind of where we're at and the issues we're wrestling with within the coalition. And then we have three wonderful speakers lined up. One from Pennsylvania, Steve Gault, one from Ohio, Bill Welch, and then an independent company with Fred. Fred, I'm going to butcher your last name, Hejazi, the CEO of Citygate. So we think it'll bring good insight to everyone on the webinar. If you have any questions, please type them in and we'll leave time for discussion. Again, our three speakers, Steve Gault is the Chief of TSMO, Arterials and Planning at the Pennsylvania DOT. In his role, he oversees Pennsylvania's performance measures derived from travel time data sets. He's been with PennDOT for 3 years and previously worked in consulting and municipal government. In his spare time, he seeks to build the next generation of data levers by stopping to extract traffic signal performance data on family trips. Steve, I can relate. As a pavement management engineer, my kids got a lesson in transverse cracking on family vacations. So I hope that you raise them well. Our next speaker comes from Ohio DOT, Bill Welch. Welcome. Bill has worked in operations for the ODOT since 2019. His current role is the Program Administrator for Data Analytics and Automation in the Division of Operations, where he helps bring data science, software development, data storage, and business intelligence solutions to life to help decision makers make data-driven decisions. Just thinking back 10 years, seeing a title like that just amazes me here today, how much data has infiltrated our everyday lives at the DOT. Bill also oversees the OHGO Traveler Information System Program. The TSMO Data Warehouse Program provides management analysis for program staff. Bill has previous work experience at The Ohio State University and in the Division of Planning at ODOT. When not working, he loves to travel, video games, and curling up in front of Netflix, which I can definitely relate to. After hearing from Steve and Bill, which I call the In the Trenches presentations, these are people working in the DOTs, tackling real problems every day in the course of their work. Fred Hejazi, who is the CEO of Citygate, is going to come back and provide a little bit overview, a holistic point of view. Fred is a civil engineer and a professional land surveyor with over 27 years of experience in information system design, software development, project management, and geospatial information systems, not to mention GPS. System design experience includes over 20 years of application development, consulting, program management, sales, and marketing experience in all levels of government in North America and the Middle East. In speaking with Fred, as well as Bill and with Steve, a rich experience set in dealing with these everyday issues related to conflation and everything you have to deal with. So we look forward to our speakers moving forward. Let's go to the next slide, please. I'm going to start with a little background, kind of where we're at in the thought process of the Eastern Transportation Coalition. We, of course, work with transportation jurisdictions up and down the East Coast and moving further west with several members. But translating between spatial data sets and bringing pertinent data, particularly industry data, to DOTs has been one of the sweet spots for the coalition. Let's go to the next slide. We put this together kind of as an introduction. Currently, it is the best of times. We have more private partner companies and vendors helping us out. I put a few of them here. You'll recognize many of these logos. Traffic information is disseminated throughout industry. It used to be the sole responsibility, or close to the sole responsibility, of the DOTs. Now we have many, many partners, many of which are just blazing trails way ahead of us. There's more and better info for the DOTs and travelers than we've ever had before. When I started in this industry, if you wanted data, you better put together a data collection program. Now you better take a look around you to see if it already exists somewhere in a much richer form than you could ever collect. Next slide. It is also, well, I wouldn't say the worst of times, the most challenging of times. We have to share this data as seamlessly as possible. This is just one example from a recent investigation into how we share mapping changes with the commercial mapping companies. Every DOT has a interface, usually a siloed custom interface to every mapping company, and they have to go through and periodically use a custom set of tools and bring it all up to date. Each data set currently requires custom vendor-specific interaction. As a rule, not everyone. There are a few emerging standards out there to simplify it, but our concern is how do we do this across the board as efficiently as possible, not only for mapping, but for work zones, for incidents, for posted bridges, you name it, more and more as this new generation of engineers and data folks come on board. They recognize that we're somewhat stuck in the old way of doing things, and we got to accelerate this and find newer and better ways of doing it. Next slide. This is kind of the world we're in it today. The common digital exchange formats. Right now, we have all the state DOTs on the left, and we have all the vendors and industry partners on the right. And every interaction requires a custom either conflation, map data update, better understand the road classes, or you're going to get confused. Incident definitions may be different. You got to create custom APIs. There's pretty much a lack of standards, though a few are emerging, and it's repeated for any new data item, any new vendor. The complexity of this increases every time you get a new DOT, every time you get a new data set, and every time you get a new vendor, more work appears. Our mission is to build effective common data exchange formats and sources so that all mapping companies have one location or portal to pick up the needed information, everyone drinking from the same fire hose, so to speak. Thank you, Denise, for that image and those words. Where we want to go is the next slide, is kind of where we want to get to. There's several things going on within the coalition. We have this little initiative called the Rosetta Stone. How do we simplify the mapping world? The Conflation webinar is a part of that today. There's the WZDX initiative coming from the US DOT that's helping to bring some sanity to this world. There's incident traffic management feeds, a rich discussion with vendors and industry. Just on a call yesterday with Waze and Ridis and several others saying, you know, is there a common set of standards that are emerging? Posted bridges is coming out of the WZDX, anything about structures for overweight, overheight trucks. And every day I hear of another one. Can't we get this to a standard digital format? What is the benefit for this? Well, once you get to a common way of talking in the middle here, it reduces the complexity of hooking up all our DOTs with all of our industry vendors and partners, and simplifies the world, reduces quite a bit of work for everyone across the board. So that's what we hope to do. Next slide. Specifically for this, need for conflation. We have multiple map databases, the state linear referencing system, which are pretty much unique for each of the states. You got US Census Bureau, USGS, you have Arnold from Federal Highway, and then you have a whole host of folks from private industry, whether here, TomTom, OpenStreetMaps, Apple, Google, traffic message channels, codes, flavors A and B, they're not all alike. And we need to create a way to efficiently translate between all of these. And that's the topic of today's discussion. We're going to have 3 speakers and each give you a unique insight in how they tackled this problem. Let's go to the next slide. I think we're transitioning to our first speaker. Steve, if you're live and have video, please take the con and take us through your presentation.
All right, I am here. Let me bring my slides up. All right, is that showing up for everybody?
Yes, it is.
Okay.
Perfect.
All right, well, thanks for the introduction, Stan. As mentioned, I'm Steve Gault in PennDOT's TISMO Arterials and Planning section, and also the MAP 21 performance measures that relate to the probe data fall under my jurisdiction as well. So kind of laying the groundwork. A lot of what I'm describing will kind of be in the context of specifically the challenges we faced with the federal performance measures, but then we're also looking to apply a similar methodology for other things. So with that in mind, really kind of what's the groundwork of why did we face this problem? What are the things that we were dealing with in Pennsylvania? So the first is the peak hour excessive delay measure, which is one of the CMAQ measures, requires a speed limit in order to calculate the delay. So that was something that was not part of the NPMRS data set at all. So we needed to make sure that we were providing a speed limit for every road segment. The next piece is that not only the PHED measure, but also some of the system reliability measures use the average daily traffic. And we had discovered that there were some errors in the conflation process that was used by the NPM RDS vendor team. In not saying anything negative about them, they were trying to do things for all 50 states and all different formats. So, we just noticed that there were some things that we needed to address to fix that data. So coming back to this, both of those data sources, the speed limits and the volumes, PennDOT has stored in our roadway management system, which is primarily a 1980s mainframe database, but there also are GIS shapefiles that are produced from that database with attributes. So the first challenge then is really the segment limits, because the TMC channels break at interchange ramps and major intersections. Just focusing on freeways for a moment, the interchange ramps are a pretty good break point, but then sometimes we get some long segments in there in some of the rural areas where there's long distances between interchanges. PennDOT's linear referencing system, our segments are usually about a half mile and break at major landmarks, so often major crossroads or bridges, changes in jurisdictions and so forth. But interestingly, the interstate segments were always set up to be a half a mile, so that they actually break on the mile markers. So we have different beginning and ending points of the road segments between the two data sources. And then, aside from the beginning and ending points being different, the geometry of the roads themselves isn't the same. They were created from different things. So if you put one line on top of the other, it's going to look like having a couple kids trace things, and it doesn't exactly match. And then the final piece is there were really no common attributes to join the data sets. We have route numbers, which can be helpful, but the format of things in one system or the other was not always consistent, and that provided some extra challenges. So our goal in doing this was to get one speed limit and one volume, daily traffic volume, that's representative of the entire NPM RDS TMC segment for each segment. So there's, that interchange to interchange segment, we wanted to have one speed limit and one volume that applied to that whole segment. When we had that, we could then produce a comma separated value file that has the TMC code and then either the speed limit or the volume or both. And then we would be able to send that to the NPM RDS team via email to replace the default values that were provided in the initial data set. So the process we used was really starting with trying to compare the line segments, and we ended up breaking the PennDOT line segments in, or I'm sorry, the NPM RDS segments every 10 feet, and then trying for each one of those points that are separated by 10 feet, we tried to find the closest PennDOT RMS line string that was within 25 feet. So, if a point was near two roads, we would take the closest one, which sometimes can happen if there's intersections or if there's divided highways. And we played with the distance a little bit as we were doing this, using longer distances, shorter distances, and 10 feet seemed to be a good balance between the processing time and accuracy. Once we had that correlation for each point at 10 feet along the segment, we would create a tally and look at that for each, and we would have that key of the PennDOT road segment that corresponds to each one of those points on the NPM RDS segments, and essentially just take a summary. This slide just shows a small example of that, but we would be excuse me, pulling whichever had the most matches would be kind of the winning segment. So we recognize that this isn't perfect. There could be cases where PennDOT's data shows that the volume changes or the speed limit changes, and we looked at potentially trying to do a weighted average, but it really didn't provide much value for the extra complexity of the process. Some of the things that we encountered along the way, the first one was undivided highways. PennDOT's system uses one line string to represent both directions. So, on a 2-lane road, that would just kind of go down the double yellow, so to speak. But NPM RDS has a separate line for each direction. So what we needed to do was take the traffic volume and divide it in half to get a directional value. We also had some non-state roads that are on the National Highway System and part of the federal performance reporting, but are not captured with the same level of detail within PennDOT system. We do have those in our RMS system because of other HPMS reporting, but they're not in the same format. The biggest example of that is the Pennsylvania Turnpike, that we treated that as a undivided road, so there was just one line string that was bidirectional. For that particular one, because of the unique situation, we actually converted that to parallel line strings first before we did the conflation. And then we also had some locally owned roads that are on the NHS. Some of those we actually didn't have speed limit data for at all, so we had to dig a little deeper to find that. As we were going through, we tried to come up with some accuracy statistics, such as the number of conflation points per TMC or the number that were associated with the winning segment, and then use that to determine a percentage. So, in an ideal situation, we would have, 100% of the conflation points within a TMC would all match to the same RMS segment, but we know that that's not a realistic thing. So we wanted to try to gauge how much of the winning value did that correlate to the overall segment length. And our overall goal was really to minimize how much manual work we had to do and really define what's good enough so that we could accept it without going through a long and intensive manual process. We have, I think, over 40,000 miles of state roads in Pennsylvania, so it could be very challenging to go through on a 10-foot basis and try to fix anomalies. But in order to do some basic checking, we created a web map with some problem locations, and there's a link here and just a little graphic of what that looks like. But we tried to flag anything that didn't have one piece or the other, whether it's speed limit or volume, things where where NPM RDS did have volumes, and we were trying to compare what volumes we were getting from our process with the volumes they had. We were flagging ones that seemed to be off a lot, and that's how we caught some of those issues that I talked about earlier. Some of the lessons learned from our process is, having more conflation points leads to better results. We started looking at going with 100 feet instead of 10 feet and found that doing that shortening of the length down to 10 feet really seemed to provide a good benefit. And as I mentioned before, the winning segment approach seemed to be providing a good benefit without the extra computational effort to do a weighted average of multiple values along the length of a segment. Some things that we're still looking at for the future is trying to formalize how we want to override values when we do find, if there's anything that we spot check and want to change. Right now we want to be at a point where we can just run the process and get the results and send it in. So if we have to run the process again, anything that we would have been manually overridden would get replaced by the process. So we want to make sure that we have a way to deal with that. And then we also are looking at how to use a similar conflation methodology to better link other data sources that can help identify congestion causes or details of what's happening on the road. So we have a road condition reporting system that our traffic management centers use to track incidents. So that's an important source for us to link together to find out when we knew things were going on. That also captures road work and construction, another critical construction piece we want to know about. Weather data is an interesting case because it's not linear like roads are, so it's introduces some different challenges for conflation. And Denise mentioned a little bit about a congestion pie chart earlier, and I'll just put a plug in here for our data analytics team. They've actually done some of this conflation with the different sources and have a pretty good working version of a Power BI dashboard that lets us dive into the congestion pie chart, starting at a statewide level, breaking urban versus rural, looking at actually down to the individual road segment. So with that, I will turn it back over for the next speaker.
And Steve, this is Denise.
Sure.
One other comment I think to make is that the CAT Lab and Michael Pack are directing and working on that TDADS congestion pie chart for the country, but you guys have done a lot of great work. And I know that there was a lot of collaboration between the two of you on getting the TDADS tool ready. So thank you for that.
Thank you, Steve. There was a couple of questions. Remind everyone this webinar setup has a chat and a Q&A. So if you have questions, please go to the Q&A. It's a bit confusing. There's a couple of questions that are related, Steve. One is, have you documented this to share? Of course, this webinar is one way of doing it. And what tools did you use? Is it ArcGIS or is it some custom scripts? If you could answer that.
Sure. So the documentation, we did have, we had some consultant help on doing the original effort, and they did prepare a document that explained kind of step by step what was done. That was actually what I used to pull together the slides. So it was a fairly simple process, so the documentation was not overly extensive, but we do have a document describing that. The question about what tool did we use, I think it ended up being like a Python script. So it was not directly in ArcGIS, but it was just pulling from the shape files with a script and then running it, because doing it manually within ArcGIS was going to be a lot more cumbersome.
We have one last question. We'll take that before getting over to Bill. So Bill, if you want to queue up and get ready, that would be great. Your last question is, you've applied this to TMCs. Have you tried it to other base maps, particularly NREX XD or anything like that?
Yes, we have. We started with the TMCs, but we have used the same process, and that was part of making sure we had it all documented so that we could replicate it for INRIX XD data.
Okay. Denise, should we take more questions or should we save the rest of the questions till the end? A little bit.
I think there's just one more right now. I think
Okay.
there's one. Maybe we could do that and then move on.
So it looks like there was a question on the accuracy rate. I don't have a specific number, but you know, we did have some of our MPOs were also doing validations and kind of looking at what we were coming up with, and they were pretty thorough in that evaluation. So we felt that once we got to the point that we weren't getting flagged for having more anomalies, that we got to that good enough point. So we don't have a specific number, but we think we're pretty close to being as accurate as we need to be.
I was going to push you on how good is good enough. I noted your, the objective is to reduce manual labor. Well, is there a objective threshold in all of that, or is it more subjective as you work with it to get it under control?
Yeah, I think it's really a matter. It's primarily subjective, but our goal is, we want to have something that's usable without becoming so costly and burdensome that we could never get to something that we could actually use to make decisions. So I think trying to find that subjective balance of being able to have usable information quickly and having it be good enough to make reasonable decisions. We're not engineering a project from this, but we're using it for a screening of identifying where we may need to do things, especially from a TISMO perspective. So we're using it to develop regional operations plans and do a planning process on where we need to be focusing our efforts.
We have one last comment from Paul, if you want to respond to it. Understanding how you did this coming from a voting system of points, maybe we should consider reporting some of these values by a defined point as opposed to a segment. And I like how he closed it. Should we have one segment to rule them all as opposed to just reporting some spatial values? If you can see the chat there, if you have any comments on that.
Yeah, I think for the federal performance reporting, the calculations are based on some definition of segments. The federal regulations do allow states to define their own segments, but I think probably most states decided to just go with the TMC segments because they were already defined and didn't require having to manipulate the data, for all the other elements. So, from that perspective, we really had to get to a point where we had to have one speed limit and one volume for the segments that we were reporting on a federal basis. And because we were using the TMC segments, that's why we had to get to having one value per TMC segment.
It's a fun thing to contemplate, but I think we ultimately come down to either point-based attributes or segment-based attributes, and just have to find a way to get between the two efficiently. So thanks.
Yep.
Good. All right. Thank you very much, Steve. Reporting from the trenches in Pennsylvania. Now going over to Ohio DOT. Bill, do you have your presentation up and ready to go? Yeah. I see your presentation.
Bill, you may need to unmute your line.
Oh, sorry, I found it. It moved screens on me when I shared it.
Yeah, it does that.
All right. Well, good morning, everyone. Thank you so much for joining us, and Stan for introducing me. I'm going to focus a little bit on our experience taming what I like to call our twin giants of probe data and linear referencing systems, and sharing kind of our best practices and takeaways from our journey going through that. So I want to start by giving you just a little bit of background about crow data here in Ohio. So we've had NREX XD data for all of Ohio since about 2017, which gives us about 170,000 segments to try and conflate. So our primary use for all this is in our traffic management center, and then for some of our operations, analytics, and maintenance operations projects. But we also have a few other users kind of in traffic modeling and signal analytics, construction, and a few other areas that make use of it as well. So now that we kind of had that, I'd also like to talk just a little bit about our LRS system. So here in Ohio, we have 121,000 plus centerline miles in our LRS, and that's 215,000 LRS segments that we get to try and match to. So with that, we have kind of two versions in Ohio. So we have our county divided version and a statewide version. For most of our internal purposes, we're using that county system, which gives us kind of a unique challenge maybe, in that we have to decide how to handle our XD segments that go across county lines and we're conflating them. So we made the decision that there would only ever be one XD segment to one LRS route. So we have to kind of account for that when we're going through our process. A second kind of aspect of it for us, I guess, is that we have kind of a mixed carriageway system. So for divided highways, we have split identifiers. We have a north and east, and then a south and west direction. But for our kind of normal two-lane roads, we only have a single identifier. So that kind of gives us a difference for highways versus, some of our more, rural roads. And then another aspect for us is, so we only have annual updates. We're not trying to update it all the time. So that makes it a little bit easier for us when we're going through everything, which is great because we also have a lot of roadways that aren't in our LRS. And so there's just some segments that don't ever get conflated and all that fun thing. So it makes it easy to maintain it for us. So there's two pieces of terminology I want to mention because I use it throughout the rest of the presentation. So one is that we call our unique LRS identifier an NLFID. So we use it here. It kind of includes the jurisdiction, route type, county, road number, those types of things, and that uniquely identifies each segment. And then we also have our measurement values called log points, which is more or less our mile markers, I guess. So like Steve kind of talked about, one of the key challenges that we came across as well was that it's spatially different from our LRS. So this is just an example from Ohio. I won't go into all the reasons that make it hard since Steve went into it. But you can see here, sometimes it's really close if we look here on the left, and sometimes it's further away. And so that just makes it a little bit difficult to actually get an accurate match. So for us, we really wanted to figure it out though. So we have our LRS, we have pro data. Why did we need to match them up? So for our office, we had two key projects that really drove this. So one was our snow and ice performance evaluator tool. So this started back in 2013 as a way to provide some guidance for our maintenance crews on how well routes are being recovered during winter weather. So this relies on speed data and road weather data to kind of say, hey, this is when there was an event, this is when it ended, and this is when it should have been recovered, and this is when you actually recovered it. So when we first started, it basically involved, we had kind of some additional staff that we would go through. We would load everything into Redis and then download the data one by one for all of our snow and ice priority routes. And by the time we got the full XD data, we said, well, we need to have something a little bit more efficient. And we really needed to figure out how to more automatically map it to our LRS. So we weren't, just loading things, for days on end. So that was kind of one piece to get that figured out. And then for a second piece, we have Traffic Operation Assessment System Tool, or TOAST. So we use this in our office. We really use it to help with TSMO funding and identifying locations for TSMO countermeasures. So we bring in a whole bunch of data from across the department. We have crash reports, ATMS incidents, traffic volumes, bottlenecks, have a whole bunch of different things that are all more or less linked against our LRS. But then when we wanted to bring in speed data and use that to inform some of our measures, we had to say, well, how do we get our speed data matched up against our TOAST corridors? So our journey to this kind of went through a few variations. So in our first attempt, we didn't really know what we were doing, but we knew we needed to do something. So we asked someone else, we said, hey, can you give us something, anything that doesn't involve us going into Redis for, I don't know, or 5,000 TOAST corridors or whatever, and trying to download everything, or I don't know, maybe 500 snow and ice priority routes. So they gave us this method to start with that was just based on the start and end latitude and longitude of our NREX XD segments. So this was definitely a great start. It gave us matches for a lot more than we would have gotten with nothing. But one of the key shortfalls it had was that it only considered something matched when both the start and end lat longs were the same. So as you can probably imagine, there's some scenarios where that doesn't work. So one being, for example, if the segment starts and ends on an intersection, a lot of times the start and end will get matched to the cross street rather than to the actual, vertical segment like we see here. But then for us, we also had an issue where, especially for highways, when we would have segments cross county lines, that would also end up getting tossed because the start point would be in one county, the end point would be in another county, and they'd have different LRS identifiers at that point. So we started hunting for something better. We kept putting off the 20.1 conflation process for a while until we had an idea. And we said, well, what if instead of just getting the closest LRS segment, we could get all of the LRS segments in the neighborhood of the start and end points. The idea was that if we saw the same NLFID in the neighborhood of both points, even if it wasn't the closest, there was probably a good chance that that's what we wanted. So we tried it out and it ended up being significantly better, but it still wasn't quite perfect. It was still off, and the perfectionist in me really wanted to have something. So when the 20.2 release came around, this had turned into kind of my white whale. I knew that there had to be a better solution out there, and we even started saying, well, maybe we could consider a consultant or a research project, but I really thought we could maybe figure it out. And finally, around 8:30, it was like the night before we absolutely had to pull the trigger on the other method if we were going to do it. It finally occurred to me that we could sample points along the inter-ring segment geometry and then use that to do the conflation. And we've gone with that method ever since. So we kind of logically separated this idea into 3 steps. So first was, well, let's figure out what NLFID we should be using. And then we'll take that and we'll figure out what the start and end log points are of the segment. And then we'll join that with some stuff and save it to our Tisma warehouse. So to do it, we developed a Python script. So we did this and then with some geospatial commands through SQL Server. And Python was the right choice for us because it already has a lot of built-in libraries for handling data and numerical analysis and geospatial analysis. So we didn't have to waste our time developing that and could focus on, this business use case. So once we did that, we kind of were able to start diving into that process. So I'm going to gloss over these next 2 slides. You're here for reference on later on if anyone's interested, but I'm going to go through an example that kind of illustrates what we end up doing. So the first part of our process was getting the NLFID. So we'd start by saying, okay, well, here at the bottom is 0%, and then we go up 10% across the line. So this would be 10%, 20%, and so on up to the top at 100%. And so we would find the NLFID at each of those points. And so here for this one, we might get that our top point is Municipal Road 4237. Our middle 8 points are Municipal Road 1342, and our bottom point is Municipal Road 451. So since Municipal Road 1342 is chosen 8 times, we'll say, hey, this is the one we're going to go with. And once we get that, we'd say, okay, well, now where do these started endpoints fall along that path? And so we get, log point 0.138 and log point 0.317. And then we would take that, join it with our other stuff, and save it. So to get to this point, it took us about 30 hours of work. So this included developing it, testing it, fixing it, and validating it one last time. So we had one person, in this case me, working on it, and so it didn't cost us any extra money to do, which was fantastic. So after we kind of got that initial version done, we said, well, we can make it a little bit better still. So this focused on 2 areas. One was performance, and the second was a few accuracy tweaks. So for performance, obviously this is great, it got it done, but it took 12 hours to run. And so it'd take overnight, and just the people in our office being busy, that just kind of hindered our ability to do testing and other stuff and required a little bit more scheduling. So we wanted to try and make it faster so we could start maybe the same day. So I'll talk more about what we did in a second, but that reduced the runtime to 1.5 hours. So we could, run it in the morning and by the afternoon, start the QA process. Then the second piece was that as we did some QA with it, we found a few more edge cases that we hadn't really thought about. So for example, NRIGS has some really, really tiny segments that tend to lie in the middle of intersections. And so if we look in here, so we might have a segment like this, but it might be so tiny that the closest LRS segment to all of those points is going to be the cross street rather than the vertical, street that we see here. And so that wouldn't be right. So we ended up looking at the direction of the segments to figure out which one should actually be right based on direction rather than just the closest point. And that resolved most of those issues for us. So performance-wise, we had two major changes that we did. So one was initially when we did this, just have something done, everything ran in sequence. So we would figure out all the NLFIDs in a chunk, and then we would get all the log points in a chunk, and then do all of the saving in a chunk. And in each step, the previously processed segments, they would just sit there dormant, waiting for something to be done to them, and that just wasted a lot of time that we could have done for more processing. We also relied on an API to query our LRS that our tech services group had put together. So that provided additional overhead just to get the data back that we needed to do the linking. So we ended up changing that. So everything now runs in parallel. So it's kind of in a stream. So every time we figure out an NLFID, that goes into the next step to get the log points, and then that gets saved. So instead of waiting around for everything to happen, it's kind of happening all in a nice little stream. We also started connecting, at least for the NLFID identification, to our database directly, which also saved, it maybe didn't save a whole lot of time, but when we have 170,000 segments, even saving like 0.1 seconds per segment saves us like 5 hours of runtime. So it saved us enough to make a significant difference. So kind of some next steps for us from here. So I think my biggest goal is to increase the number of log point samples. So Steve discussed some of their research that they've done on increasing the number of log points, and we feel the same. So if we think of a typical-ish, maybe half-mile segment, when we're only doing 10 points, that's giving us, maybe 1 point every 250-ish feet. So our next target is to kind of up that to maybe every 5% up the line. So we're doing 20, and that would give us closer to 100 feet, and see how we do with that. And then the second big piece for us is kind of our QA process. It's definitely our weakest area. What I guess passes as our QA process is kind of random. We load our finished project up into ArcMap or QGIS or whatever, and we just randomly click around the map, look at the segments, see if they conflated correctly, and then we do a few checks of some known problem areas that we know sometimes exist. So it's something, it gives us a little bit of confidence that what we did is right, but there's definitely a lot of opportunity to improve that. And for us, it's just kind of figuring out the timing to build something that does that. So at this point, you've heard we solved conflation. We did it in under 4 days with one person and no money. And like a lot of things that sound maybe a little too good to be true, this one has a little bit of a caveat with it too. And for us, we only got this to happen quickly because we had someone that understood both the technology side with programming and the data side. So if we had taken this and said, hey, we know we want to solve this, but we don't know how, and we went to our IT group and our GIS group, we definitely would have gotten there eventually, but there's kind of a disconnect, at least at ODOT. So we have our IT group. They have a lot of great programmers, but they're mostly building applications. They're building our websites and other things that we use. They're not really doing as much data wrangling. We also have our GIS group, which they're very good with geospatial data, but they're mostly doing kind of your traditional analysis and ArcMap and our geodatabase administration, and they're not doing as much programming. So there's kind of that disconnect there. And by the time we would have gotten on the agenda and went out against the other projects that need to be done and got to our project manager and business analyst and everyone together, we probably would have been looking at a significantly longer process where even me, I'm somewhat anti contracting in general, but I probably would have been willing to hire it out at that point. So also, second big lesson, you're probably feeling a sense of deja vu. We've seen Steve's presentation. You see we came up with something remarkably similar. If we had probably, called over to them, not a far way away, and understood what they were doing, we would have gotten there faster. So to answer the question from our LRS and probe data giant friends that took all of my limited Photoshop skills to put together, yes, they're officially BFS in Ohio, and we're looking forward to even some more progress with that. So thanks so much, and look forward to any questions if there are any, and hopefully I left some time for it.
Thank you, Bill. Please use the Q&A for questions. And while we're waiting on that, I had one for you, Bill. Both you and Steve commented on, how good is good enough. It's kind of an ad hoc process. Do you keep any metrics in the process saying, if you're using a voting logic or some type of matching logic, how well it matched to help screen possible questionable matches along the way, or heading in that direction?
So we haven't quite formalized it yet. So we kind of get to it through more of our ad hoc checking process. And we have a general sense of areas where things might not work as well, but we don't have it formalized. And that's something we'd like to try and get into. I guess we've kind of figured that as long as we get most of our highways and more major state routes, that's kind of a good enough point for us. So we tend to try and check those a little bit more closely than some of the other roads.
Cool. Okay, the questions are starting to come in. The first one is somewhat related to that. How much QC/QA is still involved in the cleanup work to update correct traffic volumes from one segment to another?
Yeah. So for us, so traffic volumes, I guess, were less important for us overall. So we were mostly focused on making sure that we're still just getting the segments matched. We're relying more on it for speeds than volumes. So there's still, I mean, some amount of QA/QC, but we've gotten to a point where we feel comfortable if we spend a few hours checking some areas, that it's something that's given us a good result.
The next question was a clarification. I believe you said you were conflating to INRIX XD. Did you also do TMC data, or does Ohio not work with the TMC codes?
No, so this is only XD data. We stopped using TMC data for the most part once we got XD data because it gave us a little bit more granularity for our use cases.
Okay. Good. Coming in from Paul, did you find any segments on either side that completely fell out? What did you do about that? Does the Ohio LRS go down to local streets? I guess a couple of questions in there. Of the stragglers, what do you do with the stragglers? I think is the first one if you don't get any match. And how fine grained does the Ohio LRS get to? Yeah,
so we check somewhat closely the ones that don't match, and almost always they are segments that don't have a match in our LRS. So for our LRS does go down to local streets, but it doesn't have all of them. So especially in some of our more urban areas, like up in the Cleveland and Columbus area, there's a number of local streets that we just don't have data for, and we just don't match them. So we do check them, and we maybe take a sample of them, and as long as it seems like we've got most of what we need, we call it good enough. We also have some kind of like other weird cases that we found through going through that. Like we have some weird like upper lower road configurations in the Cleveland area that also result in kind of weird matches. So we just kind of check as best we can and go with it.
Related to that, just my own personal question, did I recall correctly that this is a once a year process for Ohio, that you like to line these up and then run for another 12 months and then do it again with a new data set? Is that correct?
Yeah, so it ends up being twice a year. So we're tied to the INRIX map releases. So every time they come out with a new map that has map changes, we'll do the conflation.
Okay. We'll pause a few more seconds to see if any other Q&A come in while we're queuing up the next presentation from Fred. I'd like to thank both Steve and Bill. I always love hearing stories of I call it in the trenches. You have to get a solution. How do you get the solution specific to your state DOT or to your roadway jurisdiction? Those are excellent examples. Our next speaker, Fred Hejazi, has experience, maybe not directly working for within a DOT, but for working with several government agencies that had to do similar things across a broader scale of geospatial mapping systems. So seeing no further questions, let's switch over to Fred. Fred, are you live with your presentation? And do you have your volume on?
Fred, you're muted. If you would like us to share the slides, we can.
Sorry, I was building anticipation. No, I'm trying to share this PowerPoint and it's going to the wrong screen. So if you just give me 1 second, I will get it working.
Great. We're seeing your whole desktop at this point.
Did it come through?
No, we're seeing the presenter view. There you go.
Perfect.
Thank you.
All right. Sorry about that. So I do actually have transportation experience. So it is, I have done work in the transportation. Most of my experience has been in other areas, but I've done quite a bit of work for state DOTs as well. So sure why this is not going. All right, so just a little bit about our company. We are a geospatial software development company. We've been around since 1986. We're located in Annapolis, Maryland. We do most of our work in ESRI technology, so we've been a business partner with them since 1999. We primarily develop applications on the desktop and the web using ESRI and Google Maps. And I was the software architect for our Conflation product. I was also the product manager or the project manager for a 6-year Conflation project for the U.S. Army Geospatial Center that essentially formed our Conflation product. So how we came into Conflation was we did a lot of manual conflation of 1990 Tiger files to 2000 Tiger files. So after having done all that manual work, we started to think that maybe what should exist was a completely automated conflation tool that you could give 2 data sets to, and the software would kind of figure out which road was which and really be able to solve the conflation problem as if a person would do it. So back then, most people were using proximity as a means of conflation. So they would match one data set to the other data set based on how close the geometries were. So we decided to do what we call the statistical best match, which I'll explain in a minute. But after we had developed the product, we introduced it in 2004 at the ESRI user conference. And somebody walked up during the conference with a file and asked us to process it. We processed it, put the results back on, back then they were floppies, so we put it back on the floppy and gave it back to them. And a few months later, we were invited to meet with the US Army, and they told us they had been working with Northrop Grumman for about 6 years, and their matching technology had never broken 65%. And we hit it into almost 90% on our first match. So what ended up happening was they canceled Grumman's contract and gave it to us. And as I said, we continued to work with them and really develop the technology as quite a bit further. As I mentioned, most of the conflation technology back then relied on proximity. So you'd buffer lines, you would try to find what is the nearest set of lines to it, and then you would essentially match that way. We couldn't make this process work where geometric errors were inconsistent. So if you had one area where things matched up really well, other areas where things were quite a bit away from each other, that process didn't work. It also didn't work if the scale between the data sets varied greatly. So if you were going from something that was 1 to 100,000 to something that was 1 to 2,000, it just didn't work. So because we were using a statistical best match, it was very similar to how a person determines matches between two lines. So the software looks at proximity, network connectivity, directionality, length, and feature type, if feature type is available. And then based on all of those, it tries to figure out what is the best match between two different segments. And then from those, it picks up what are the most likely matches between two data sets. So as I said, that allowed us to solve a lot of different conflation problems, the biggest one being scale difference. The example on the bottom left, you have two data sets that are completely different scales, and we need to identify the roads from one data set to the other. And again, I want to emphasize that this was a completely automated process. So the user would just tell the software, here's the starting, this is the source data, this is the target data, and then push a button. And then the software would go from there. We could also handle density difference. So if we're going from a data set that was just major roads to a data set that included local roads, even if there was no attribution that matched between the two, we could match those using this process. Accuracy difference, again, the bottom left was an example where in some areas the data set matches quite a bit better than other areas. So in the upper left side, the lines are pretty much on top of each other. As you get further towards the bottom right, they tend to get further and further away from each other. The geometry is still the same, but the lines are not in the right place. And lastly, we were also asked to handle situations where the source material is completely different. So we were asked to go from diagrams, hand-drawn diagrams, to actual maps. So the software would have to be able to figure out based on how a drawing, sketch drawing, was created to something that actually was based on scale. And what they gave us as an example to process was the DC Metro map, which is on the bottom right. So as I mentioned, we worked with them for about 6 years. We ended up creating a product called Conflex, and the bottom screen is the screenshot from the product. We eventually ended up also creating an ArcGIS add-on version. Now, the key thing about how this product worked, it was very focused on what is called a best map. So the Army had a very specific definition for what a best map is. A best map for them was an aggregation of data from the source, the target, and the parts that matched. So essentially, the reason why they wanted to create this best map product was that in situations where they would be going into an area where they didn't have very good maps from the from MGA, they would get maps from the Europeans, they would get it from the Russians, they would also get whatever was available. Then they would try to identify all of the lines that matched across all of those data sets, and then enhance it with all the lines that were not in all the data sets. So the key thing here was to remove all the duplicates, but merge in all of the data from the various sources. So that in that kind of an exercise, the software worked very well. It was able to identify those and merge the data together. But this type of an approach really fits to a very narrow group of projects. It provided rapid results, which is one of the things that they were looking for, because they, you know, in a situation where they're going into an area, they don't have 6 months to produce maps. So they wanted something that could work overnight and generate actual results very quickly. But what it was not good at was solving some of the linear referencing and route name combination or address ranges. So in the example below, which some of the other speakers have also brought up, if we're going from the line at the top, which is in green, to the one in the red, you have different nodes on the bottom ones, and different breaks in address ranges and linear referencing systems. So we would have to actually go in and write additional routines that would, once the match is done, for it to go ahead and segment the data appropriately for this type of work. The other part of this was, because the Army wasn't interested in doing a manual review, we could give them a percent accuracy, but in a lot of state and local conflation, they want everything to be 100% matched. So you can't live with, well, this is 75% or 80% matches. So where are we with this now? For people that are interested in an off-the-shelf solution, we allow customers to do extensive usability tests. And we've had a lot of people who had good success. We had the Weather Service in Canada do a countrywide conflation. They were only interested in road names. So they brought the road names from their old system to the new system, and they used the software fairly successfully. We also built a set of internal software code that we customize based on project requirements. So our goal is to create a specific tool that allows regular matching between two different data sets. And that tool has to be customized to the specifics of the requirement. Then we integrate that with ArcGIS for manual editing. And one of the ways that we've been able to really increase the software's productivity is by allowing a semi-automated process. So the software runs through its automated routine. The user goes in and corrects some of the mistakes that the software has made. The software then uses that information to do additional matches. And we do this through an iterative approach, so that each cycle the software gets better and better at making matches. And I guess with that, I would like to open it up to questions.
Thank you, Fred. We purposely staged this, hearing from a couple state DOTs and then from Fred, who's had experience across many industries. And I think it gives you great perspective on both the uniqueness of the LRS system and its challenges relative to other application areas. I sure appreciated that. The statistical match really harmonizes with how Pennsylvania and Ohio use some voting logic, breaking up the segment into multiple points, and then taking a look at the voting logic for there. Kind of pausing a minute to see if we have any questions coming in for Fred, or any questions in general for our panelists at this time.
Stan, while we're waiting, I think it also should, everyone should know that within the new marketplace RFP that we are building right now, there is a data section for conflation. So it's nice to see this work going on, whether it's through the states or through Fred. But again, know that we are looking at this as a serious data set to be offered through our marketplace. Okay.
Thanks for that comment, Denise. Even as I think it was both Bill and Steve commented, they were contemplating going out for outside help, as well as doing it internally. And they ended up doing it internally, but both are valid, and we're trying to create smooth pathways both ways. Fred, we did have our first question come in. What ground truth was used to reach the 88% accuracy? I think that's a general question of, well, how do you determine equality, and how was that originally defined? Did you assess that, or did the Army?
No, the Army assessed that before they actually even contacted us. So what they did is they gave us a data set that had been manually conflated, 2 data sets that have been manually conflated with each other, and they essentially had a link file between the two. And then after we generated it, they compared our results to their own results.
Okay. So the ground truth was the manual processing, I understand.
Correct. The ground truth was the manual process. Now, when we run our process, we do generate a percent match. So we generate all of the data sets that all of the features that matched 100% that we're confident with, and then there's ones that we're less confident with. And the software generates a link file accordingly that has that information in it.
James, I think that answers your questions. If you have any follow-up, please type it in.
And his question about he had a second question about how the QA/QC was processed. Is that just answered?
I believe it was specific
Okay.
to that first 88%, as well as the comments from Fred on how they do link percentage matches. I don't think the QC/QA is if you have a link match, how good is that match? What are the secondary possible solutions? But how many of the, if you have 1,000 links to match and you're able to do 950 of them automatically, that's where Fred's software is coming in at.
Yeah, and if I can add, for anybody who's looking to do conflation from a process perspective, what we found in general is that you get the best results when you look at the network. So not proximity, but when you look at the network. And through that process, you can identify all the major roads and their main intersections. Once you have that information, then you can go through and match the lines together. Even if they have multiple segments that don't match, you at least know where the beginning and the endings are. After you have that, you can work out this secondary roads. Once you've matched the primary roads, then you can match the secondary roads. The process becomes much easier. So that seems to be the way that we've had most success with conflating large data sets.
Questions coming in for Paul, and I think it's to anyone that's presented here. Has anyone tried using sources such as OpenStreetMaps? That's getting ever more popular as the basis for their LRS. It seems some data providers are using that to report some data. I believe so. It's free. That's what all the college grads are using. So you're going to see it more and more in the marketplace. It comes with its own issues, and there isn't command and control over the segmentation. So maybe it's a non-starter for people. Fred, do you want to take that one? Have you done any OSM work and compare, contrast it against other map bases?
Not. One of the disadvantages that we had was we were working in a classified environment. So we would throw stuff over the fence. We never knew what happened to it. So we didn't see necessarily where the source material was coming from. It could have been from OpenStreetMaps, or it could have been from any number of places. And then we would process it and throw it out. And a lot of times they would even change the coordinates so we wouldn't know where the actual work is. And in the private side or the civilian side, we haven't really done anything with OSM.
I'd invite Steve and Bill to unmute if they've had any experience with OSM. I know we contemplated that in the Eastern Transportation Coalition's Traffic Data Marketplace, asking vendors to accommodate OSM moving forward. So it's definitely on the radar for a lot of roadway jurisdictions.
This is Steve. We have not done anything with that in Pennsylvania at this point.
Yeah, we haven't either. We've thought about it. Like I know NREX, for example, they released some open LR data that's supposed to work with OpenStreetMap, but it always seemed to me, and maybe I'm just not seeing into the future enough, that we would end up conflating to OpenStreetMap, but then still trying to go from OpenStreetMap back to our LRS. So I didn't see that it saved us any time necessarily.
We'll leave the Q&A open for a couple more minutes. I heard the term open LR, and I'll throw it to Fred since you have vast experience. Is there any generalized standards in the base, in the GIS mapping base to encode segment-based information that's more portable. I'm aware of the Open LR standard, but that's about the only one I'm aware of.
I haven't come across anything, and most of what we have seen in a lot of DOTs even local jurisdictions, you have 5 different departments using 5 different sets of data. And it's very difficult to get any way to move off of theirs, even with the LRS stuff. Sometimes there's multiple versions of it. So it would be great if there was a standard.
All right. At this point, Denise, the Q&A has calmed down a little bit. I want to thank our presenters, Steve, Bill, and Fred, for a very rich discussion on conflation and where we're at, some of the principles, some of the geometry to keep in mind. So turning it back over to you, Denise, for any last comments.
Thanks, Dan. No, I think thanks everyone for joining. I hope that you found it enlightening and educational, et cetera. I know that our process is such that we will have these slides and a link to the recording available. It'll come through via email with a link to where you can access it if you need it for references. It does take a couple weeks to do that. I know sometimes I'll get emails about, can I get this? You know, when can I get this? Typically, it's about a 2 or 3 week process to do that. And then they will reside on the slides will reside on our website. So again, Stan, thank you for facilitating. Again, Steve and Bill and Fred, thank you again for doing a great job on the presentations. And hopefully you all have learned something today, and hope you have a great rest of the day. Okay, with that being said, I'm going to sign off. All righty. Bye now. Thank you.